Hey, hello there. Today I'm looking at question 444, sequence reconstruction. It's a much disliked problem. It has 888 dislike, twice the time compared to the question number. So that tells you how bad it is. Let's read the problem. Check whether the original sequence ORG can be uniquely reconstructed from the sequences in the list 6. The original sequence is a permutation of the integers from 1 to n, so it has to have exactly n numbers there, and they have to be every number has to be unique and in range of 1 to n. Here is the range of n, so it could be quite large, quite long, the sequence. The reconstruction here means that we want to build a shortest common super sequence of the sequences in the 6. So it's going to be a long sequence that if we look at the relative order of numbers in every sequence inside this list of 6, the order of those numbers has to be exactly strictly followed in the super sequence. We will see that very clearly in the example. So we want to do two things. One is the feasibility testing, whether there is one, and the other thing is the uniqueness. So if there exists this kind of a super sequence, is it the only one that satisfies that? And if it's the only one satisfies that, the third thing we want to do is compare that with the original sequence to check whether the original sequence is indeed the only super sequence that satisfies this, this condition here. So that all the sequence inside the list is a subsequence to the original sequence. So it's kind of mouthful, and when you read it, that's kind of like tongue twisting. Let's read an example and see what it means. So the original sequence 1, 2, 3, which is supposed to be the super sequence for all the sequence inside this list, we can see that it's indeed that 1, 2, we have 1, 2 in that order. 1, 3, we have 1 that's coming before 3 in this original sequence. So it's indeed for the if we only looking at the super sequence testing, the original sequence here definitely satisfied that condition, but it's lacking the uniqueness because 1, 3, 2 also satisfy that. We can have 1 that's coming before 2 in the super sequence. We also have 1 that's coming before 3 inside this super sequence. So 1, 2, 3 and 1, 3, 2, they both satisfy the super sequence testing. So 1, 2, 3 is not the unique one. How can we tell if it's not unique? Just looking at here, we see that 1 has to come before 2, 1 has to come before 3, but there's no information about whether 2 and 3, the relative order of 2 and 3. So if 1, 2, 3 is valid, we can just swap 2 and 3 because there is no information about their relative ordering to get another valid super sequence. So we have to have enough information about the pairwise relationship between all the numbers there. So 1, 2, and 1, 3 simply is lacking that piece. So if we look at the second example, 1, 2, 3, the sequence list of sequences is only 1, 2. 3 is not mentioned at all, so we have no information about where 3 should be. So it's definitely a false. It's okay in the super sequence testing, but it's lacking the uniqueness. For question 3, we have 1, 2, 3. Again, the same original sequence. For the subsequences, we have 1, 2, 1, 3, and 2, 3. Here, the additional information is telling us 2 should come before 3, so that we can guarantee, it's guaranteed that the 1, 2, 3 is the only unique one that satisfied the testing. So that's what this question is asking. So let's look at some graphs. We have what I have here is a longer one. So the original sequence is 1, 2, 3, 4, adding one more node, and the sequence we are looking at is 1, 2, 3, 1, 2, 4, and 3, 4. Notice that if we drop the 3, 4, so by removing this link, it will be similar to the case of 1, 2, and 1, 3. We are okay in terms of only 1, 2, but we are not sure about 3 and 4. The way to look at it is that once we know that we should start with 1 because there's no number that come before 1 in this list of sequences. So 1 has to be the first one inside the original in the original sequence. once we cleared 1, we see that the immutative number that followed up 1 has to be 2. And after we look at the 2, there are 2 options, either 3 or 4, and there are no information about whether 3 should come before 4 or 4 should come before 3. So that's why we are confused, and we are not sure that 1, 2, 3, 4 is the only unique one that satisfies this condition. If we introduce one thing here, 3 to 4, so when we are at node 2 here, we see we can go to 3, we can go to 4, but with this added information that 4 still have, excluding this node 2, 4 also have some other nodes that should come before it, come before it. So it's not the time that we should really go to 4 yet. So that's telling us, with this additional information, we know that the only possible next number in the ordering, or the, here is a graph. It's pretty obvious. The only possible next node that we should explore is node 3. So if we draw a line here, so basically each line is separate. Between each line, there is only one node during our traverse. The only order that we're going to do is 1, 2, 3, and 4. So if we do BFS search, the queue is going to only contain one number at every iteration. And the time that we determine whether we can put the node at the back of the queue is when the integrate drop to 0. So we see that node 1 has no integrate, so it's not our starting point. There is no number that comes before it based on the list of sequence. So we start from there. We drop the integrate for node 2. It's actually parallel links, so you actually have 2 links. My drawing here only show 1, but it's basically going to drop the integrate for node 2 to be 0, so that we push this onto the queue and try to explore the possible next steps. We can drop the integrate for node 3 by 1, drop the integrate for node 4 by 1. By dropping 1, node 3 actually becomes the node with no prior numbers that should come before it, so we can put it onto the queue. But for number 4, it's not the same case. It's not the same as number 3, because we know with this additional sequence 3, 4, there should be something that we should visit before 4. So just by looking at node 2 and its out edges, just excluding this out edge, node 4 still have something that should come before it. So it's not the time that we should visit it yet. So that's basically saying it's not the time that we put node 4 onto the order. We have to wait until all the stuff that's been cleared. So summarize, what we'll be doing here is that we're going to do the BFS search kind of topological sort code. It's a little bit funny that usually for BFS search you have multiple nodes in each level, but here we only have one node per level. And is there any time that like excluding 3, is there any time that we find during the BFS search we actually have 2 nodes on the queue, it's going to be indicative of there is a violation of the uniqueness of this super sequence, because we can just swap 3 or 4, to form another sequence, super sequence that also satisfies this condition. Yeah, so that's it. We're going to do the graph processing to convert this sequence into edge list. So the prior nodes were pointing to the next node. So converting this list of sequences into the adjacency list, and also count up the number of integrators for every node. And then starting from the only node that has no integrate as the starting point, and do this level by level traverse. Every time that we visit a node, we drop the nodes that this node points to, drop those integrate by 1, and then whenever we find a node that was after this modification, another node has the in degree 0, we push that onto the queue. Anytime that we have a queue with more than one node, that's indicative of the ordering is not unique, so we can actually just exiting early. So after we collecting the, if it's indeed a successfully done this BFS search, we can just compare the order with the original sequence that's provided to us. So if the two match together, it's a sign that the input supersequence is indeed the only one. So that's that. So let's code this. It's going to be quite a lot code. So we're going to grab the m from the original sequence and then initializing two things to hold the outer edges and the in degrees. So these are the graph processing code. One additional thing that we can do is to handle the case like 1, 2, 3, 2, the example 2, where we just don't have enough information about the number is simply does not existing in the list of sequence. So we can actually exit early here. So that's by count the nodes from the sequence. You can do a reduce set.union. So we basically are counting the number of unique nodes inside this list of lists. If this is not the same as the original, that means we're lacking information about the particular number, so that we don't even need to do BFS search at all. So this handles the edge case. After that, we must have enough information. We must have information, at least the partial information about every node. Then we try to see does it violates the uniqueness. But before we do that, we have to generate the graph. So for every node, the out edge is initially empty. We're gonna do that for all the nodes. And the in degree is 0 for all the nodes. So we're gonna do for seek in 6 and for the from to node in the zipping these two together. So we're comparing the adjacent two numbers. Number 1 will point to number 2. Number 1 will point to number 3. Number 2 will point to number 3. So use this to create the out edges and also populating the in degrees. So this is graph processing. We created the in degree count and also the out edges, the adjacency lists. Now is the uniqueness test, BFS search, to find the unique topological sort order. So we're gonna start with a queue. That's the initially it has to be the only node with no in degree. So it's gonna be set nodes dot difference. Let's just do a list comprehension. Node in or if node not in we can do a simple test. If we have multiple nodes in the beginning that have, we can do that in the loop. If any given time in our BFS search, the queue contains more than one node, that means we have insufficient information about the relatively ordering of those nodes inside the queue. We can just simply swapping those in the topological order to have the the super sequence to be valid for that super sequence test. But it's not guaranteed to be. It's not going to be unique. So that way we can exit early. If it's indeed just one node on the queue, we can continue the BFS search. Since that we only have one queue, pop from left or right doesn't really matter. It's going to be the same time complexity. So I don't even bother to use a deck here. So what we're going to do is to decrement all the nodes in the seconds that this node is pointing to, decrement the in degree. So if the node has 0 in degree, that means we can put it onto the queue. So if any iteration that we actually put more than one node onto the queue, it's going to be catched by this conditional check here and exit early. If we successfully done this, we should have a order here. If we successfully completed this, we would just compare the order with the original. Let's see if it works. Nope. It's indexed from 1, so plus 1. Plus 1. Well, would this work? Yeah, it will work because this will actually have a key 0, but 0 is not going to be in the org, so you should be fine. Yeah, okay. Let's throw in some more test cases. Let's see, we have 1 and the input is empty. 1 input is just 1, or we will have the 1, 2, and all we have is just a 1. Let's see if it works. Okay, seems good. Okay. All right, so that's the BFS search solution to find the unique. I've been trying to avoid talking about this topological ordering, but it's essentially what this question is about. But you don't have to know this topological sort to be able to progress in this problem. By drawing out the node here, looking at just play around with the list of sequence to see with what list of sequences you can actually guarantee to have a unique order here, super sequence. You can figure out that it's essentially doing BFS search and see, do you have exactly one node per level. Yeah, so that's that. Let's talk about the time and space. Here you can see that the space and time for populating this is going to be upper bounded to be time is going to be upper bound to O square or V square. So in the worst case, it's going to be like 1, 2, 1, 3, 2, 3. Any given pair of integers will have this direct ordering, so it's going to be V squared, and potentially even worse than that, right? We can have, for example, here we could have 4, 1, 4, 5, 4, 2, 4, 6. We can also have 4, 1, 5, 4, 1, 2, 4, 6, 3. So let's call that we have n different sequences. call it S, the number of sequences we have, and the length of that sequence, SL. That's the time we need to process this, the time. For space, we can see it's linear, so it's number of on space for this graph processing part. This part, I think it's the same. So let's just actually, yeah, it's the same. We're reducing this, so we're doing the union would do linear time with respect to the length of the individual sequence there. So we have S sequence, each have a L, so this is SL time. Space is ON as well. So that's the same for both edge case handling and graph processing. So those two, the time complexity for that is there. For BFS search, we're gonna visit every node exactly once, but for every node we potentially need to look at all the odd edges, so that potentially be the same number as number of nodes. In the worst case it will be like 1 2 1 3 2 3, those kind of situation. So let's just say that the time complexity, worst case time complexity, is n squared, and the space is constant. Or if you want count the space that holding up the order here, it will be ON. Alright, so that's the analysis for 444. Actually not that bad. The question description can definitely be better. So let's do a downvote and see. The description is unclear. Okay, so I just destroyed the perfect multiplier. Anyway, so that's the question today.